xk into hk. Yk is equal to xk into hk. This is into. So now you understand that what we will do is, in case of frequency domain analysis, what we do is we find out this xk and we find out this hk. We multiply both of them, so we get the discrete Fourier transform of the output sequence. Fourier transform of this yk, and I will get yn. I will get yn. And how inverse discrete Fourier transform is taken? Simply yn, if you want to calculate, then this is equal to 1 upon n, and then summation yk e to n minus 1 e raised to the power j 2 pi by n into small n into k. Okay, this is my inverse discrete Fourier transform definition. Where capital N is the number of samples, you can say safely what is capital N? Capital N is the number of segments in which the 2 pi interval of frequency has been divided. Number of segments in which 2 pi interval of frequency has been divided. So this capital N will be given to you, that you have to take 3-point IDFT or DFT or 4-point IDFT. So this K, this N is always known to you. So in frequency domain, this is the situation. So now coming back to PowerPoint, coming back to this, let us see the transfer function. Acha, one thing which I forgot here, just one thing. If this is the situation which you have seen, so this is regarding the DFT. However, if I take DTFT, discrete time Fourier transform of a sequence, discrete time Fourier transform of sequence, then that is denoted by things like h omega or x omega or y omega, things like that. This is the notation, first of all. Suppose these are the sequences, xn is a sequence, or yn is a sequence in time domain, or hn is a sequence in time domain. Then if I take discrete time Fourier transform of these sequences, then they are denoted by x omega, or h omega or y omega correspondingly, whatever. And this fellow h omega, that means this is the DTFT of hn. जो उसका impulse response था, whatever was the impulse response of the circuit, उसका DTFT is denoted by H omega. Okay, this is also called the frequency response of the circuit. X omega की बात, इसे H omega की बात कर रहा हूं मैं सिर्फ. Only I am talking about H omega now. H omega, ठीक है ना, is called frequency response of the circuit. So this is the situation, because it's a function of omega. And you must have been knowing that there are 4 types of filters in signal processing: low pass filter, high pass filter, band pass filter, and band stop filter. These are the 4 types. Of the system is very small. When the bandwidth is of the circuit is very small, then it is called notch filter. These are the 4 types of filters. And suppose there is a filter. Now the situation is like this, that this is a filter and impulse response happens to be Hn, and let us say I take the discrete time Fourier transform. So this is the frequency response H omega. This H omega fellow is complex function of omega. H omega is called the frequency response of the circuit. It is a complex function of omega. It contains J. ठीक है ना? It containing a term of J. तो ये इसलिए इमेजिनरी फंक्शन है ओमेगा का. तो अगर इमेजिनरी है तो दिस H omega can be broken into 2 parts: mod of H omega and angle of H omega, phase of H omega. Each of them can be plotted with respect to frequency. I can plot mod of H omega with respect to frequency. I can also plot angle of H omega also with respect to frequency. Okay. And this H omega is a continuous function of omega. That is also, let me tell you, that DTFT is, whenever you take DTFT of something, that is a continuous function of omega. So this mod H omega, whatever it will come, it will be a continuous function of omega. Continuous, not discrete. Continuous function. And similar is the case with this fellow. This is also a continuous function. Now, as I told you that there are 4 types of filters. First one is low pass filter. So low pass filter has got this type of response. You know, this type. Ideal, whenever I say this, I'm talking of ideal filters. Practical filters do not have this response. Such a nice response that is not possessed by the practical filters. Because, see, what is happening here? This is mod of H omega I am plotting of the filter. Okay, low pass filter. So that means if frequency from at minus omega c to plus omega c, that will pass through the filter. So this part is called pass band. This is called pass band of the filter. And this part, other thing, this thing, that is called stop band of the filter, where omega c is called the cutoff frequency. Cutoff frequency in radians. Units of omega are radians. Are you getting? This is the frequency response of an ideal low pass filter, discrete low pass filter. This is also the continuous low pass filter, which is made using op amp, or simply suppose you take this. But this is a practical filter, which I am telling you now. It is no longer an ideal filter. When you put R and C, and you just a minute.